So the first thing I want to address before we get into substitution is this concept of an indefinite integral. What we've been working with the last few weeks were definite integrals. And a definite integral was an integral that had bounds. A definite integral is an integral that has bounds, which means it represents a defined region from 0 to 5, -3 to 2, a region of area. An indefinite integral is just an integral without bounds, which means it no longer represents a region of area. Okay? Well, the good news is we still evaluate it the same way. Think about this. When we evaluated integrals, we said take the antiderivative and then plug in the bounds, right? Take antiderivative, plug in bounds. Well, if there are no bounds, that just means we skip that step. So, in general, an indefinite integral is notation that just tells us to take the antiderivative. Find the general antiderivative. And when we go back to general antiderivatives, we need to remember now to put our plus c at the end. Remember we said anytime you take an antiderivative, we don't know if there was a constant, so we need to make sure we represent that. Well, if we're not plugging in bounds, we need to put that plus c there. So look at these three right here. No bounds, no bounds, no bounds. Meaning they're just saying, find the antiderivative, instead of having to spell it out in words. What is the antiderivative of sine of u du? What's the antiderivative of sine? Go ahead, Hayden. Perfect. So negative cosine of u. I know I don't need the parentheses. They used them, so I used them. So the antiderivative of sine is negative cosine. And because it's now representing a general antiderivative, we'll see. Okay. Well, let's take a look at the next one. It says we want the integral of 4 over t minus 2 dt. What's the antiderivative here? Or let me rephrase. What's the parent function here? If you move the 4, maybe that helps. But what's the parent function? 1 over x, the hyperbola in quadrants 1 and 3, right? It's been moved, it's been stretched. What's the antiderivative of 1 over x? The natural log. And we'll stick some other stuff in there, right? So here, this is just a little warm up here. So the 4, if you wanted to move it, great. So now we've got a 4 times the natural log of the absolute value of t minus 2. Let's see. So this right here is just kind of review of antiderivatives that we know, tied with this new concept of an indefinite integral, an integral without bounds. Let's take a look at the third one. We've got a quotient. And with what we know right now, we cannot have any quotients. Right? That was good news for us. I said, we don't know that much. What can we do with something like this? Do the heart thingy. We haven't talked about a substitution yet. We'll get there. We'll get there. But one thing we can do, this is just kind of an algebra 1, algebra 2 concept, is say, hey, if you're dividing by x cubed, now I'm going to leave my integral symbol there because I'm not taking the antiderivative yet. Then let's just draw the heart. Let's split it up. 3x squared divided by x cubed reduces to 3 over x. Plus 7 over x cubed can be written as 7x to the negative third. And then I've got my dx at the end. So we had a quotient for us, so we said we can clean that up. And now we can take the antiderivative of each piece. Now it is something we can work with. Plus 7x to the negative 2 divided by negative 2 plus c. A little sloppy, I'm sorry. So 2 takeaways here right now. Number 1 is that an integral without bounds just means take the antiderivative. So make sure we're adding a c again. And then just kind of reminding ourselves of if you have a quotient, split it up if that's possible. If it's something we memorized, we do that. Don't forget about those things, okay? All right. So now let's get into the meat of what we're doing today. What if this was flipped over, right? So when you look at our next slide, it's the same function. It's just been flipped over. 3x squared divided by x cubed plus 7. You can't split that up. There's no rule, don't draw this, but there's no rule in math telling us you can draw an upside down heart. There's no mathematical reason that we can do that. So we have a quotient. We can't factor this. We can't reduce it. There's nothing to simplify. And this is the kind of problems we get stuck on. Okay. So yes, simplifying will always be the first route we want to look at, but sometimes we just can't simplify it. So today, we're going to look at something called integration by substitution, which some people will call for short U substitution, because we are going to use the letter U. Essentially, it's going to, I know that's when John picked U earlier. I'm like, oh, perfect. Essentially, we are going to reverse the chain rule today. It doesn't feel like necessarily for some of us, it won't feel like it was a chain rule problem, but it does reverse the chain rule, and we'll see that by checking. But the idea is we're going to take an integral that's kind of messy, and we'll see some messier, integrals, and we're going to make it look easier to us by taking out the messy piece and replacing it with a single letter, like a U. Now, here's the deal. If we start changing the x's to u's, we have to even change the dx into a du, and I'll explain how to do that. So here's our goal. Change all the x's and dx's into u's and du's, because our variables have to match, okay? So we're going to still do this one. I think, did I give it to us on another slide? Perfect. All right, so now we have more room to do that. Now, at first glance, you're going to go, I don't know, what's the messy piece, right? I put that in quotes because to some people, some things are messier than others. This one, I'm going to go ahead and tell you what we're going to pick, and then we'll talk about how to choose. Let's do this. Let's pick U is equal to x cubed plus 7. Again, we'll go back and talk about why I picked that, and we'll come up with kind of a rule. But to me, a cubic is always going to be messier than a quadratic. It's just bigger if the exponent's higher. Okay, so the next thing I'm going to do, and you're going to go, why? Just hold on. The next thing I'm going to do is take the derivative. You're like, wait a second, Mrs. Patton, they're asking us to take the I know, but I'm over here. The derivative would be called du dx, right? The derivative of u with respect to x. I'm not calling it u prime on purpose. So du dx is equal to 3x squared. Do you remember when we talked about differentials back in December? We can start moving some things around. Let's do that. Let's multiply both sides by dx. And let's change this from a derivative into a differential. And I know you're still going, what the heck are we doing? Just give me a second. Because you remember on the last slide, I highlighted that phrase that said change all the dx's into du's. Isn't this now an expression that relates dx and du? Let's take it one step further. Let's go ahead and divide the 3x squared to the other side and say dx equals du divided by 3x squared. I'm circling that. You don't have to. It's not our answer. We're going to come back to that, though. So here's what I have at this point. I know you feel like we haven't gotten anywhere. We have our expression for u, and we also have an expression that relates dx and du. So here we go. Let's go back over here to what they finally asked us to do. Remember that we called this u. This is like a big puzzle, by the way. We're just trying to find a place for everything. So we've got our integral symbol. And in the bottom, I'm going to change that to a u because, well, that's what we said u equals. Now in the top, I still have a 3x squared. I know that's kind of bizarre. Just hang tight for a second. And then at the end of this integral, I have a dx. What does dx equal? It equals du divided by 3x squared. So right now it looks odd because I've got two variables in there. I get that. I think you all see it right away. So I replace this with u. I replace this because I have an expression for dx. The 3x squared, I didn't have anything for it. However, boom, boom. Oh, it's gone. So while at first it was kind of odd that we had extra variables in there, not anymore. What's left in my integral is a 1 over u times du. Now that we can take the antiderivative of. This is something we have memorized, and it's also much simpler than the one we started with. The antiderivative, we've already said, is the natural log of the absolute value of u. We'll see. But if we think about it, they didn't ask us from the beginning to find the antiderivative of something of u. They wanted us to find the antiderivative of this function of x. So at the very end, let's go put our x's back in. Remember, u equals x cubed plus 7. So my final answer is the natural log of the absolute value of x cubed plus 7. We'll see. So we started with a quotient. We weren't able to simplify. I kind of told us what to use for a substitution. We made all the little pieces go away. We kind of found a little puzzle piece for everything. And then we got to a point that was very easy to integrate. The great news is we can always check them by taking the derivative. And I'm going to do that very quickly. Now, the thing was, you're going with the absolute values. We're like, wait, I don't know what to do with those. So let's ignore the absolute values just real quick. The derivative of the natural log of something is 1 over whatever's on the inside. And then the chain rule says multiply by the derivative of what was in the inside. And then the constant goes away. Isn't this what we started with? Right? So when we think about like, well, we started with a quotient, it feels weird to say we reverse the chain rule. Yeah, but when you use the chain rule and you multiply by the derivative of the inside, that can create a quotient. And that's what happened. Okay. All right. So that was just our check. We can get rid of that. This is our answer. Okay. Good. Let's do another one. So we've got the integral. This looks a little messier, of x plus 1 on top. And on the bottom, we've got that quadratic squared. Now, again, I'm not stopping you from trying to simplify right off the bat. You want to try to factor the bottom? You can. In fact, it does factor. It factors into x plus 3 and x minus 1, I think. But does that simplify anything? No, because the top is x plus 1, not x minus 1. But don't not think about that, because I think that would have made it easier if we could have simplified. So again, this is kind of messy. We've got a quotient that we can't simplify. No one wants to multiply out the bottom, I don't think. So let's make a substitution. Let's be smart about it. Remember, we want to pick the messier piece, but we don't want to pick something too crazy. So if substitution is in fact the reverse of the chain rule, listen to the phrase that we use with the chain rule. Multiply by the derivative of the inside. I use that phrase so much. Inside, inside, inside. Maybe that means what we pick for u should be what's on the inside of something. Inside parentheses, inside a square root, inside a trig function. And so when I look at this one, I see some parentheses. So maybe I'm going to start with what's inside the parentheses. And it may not work, but I'm going to start with u equals x squared plus 2x minus 3. We don't know until you do these for a long time. You don't know if this is going to work right off the bat necessarily. So it's kind of a let's guess and check kind of thing, which is kind of a struggle. We'll talk about this in just a minute, about how you kind of might know. First step, take the derivative. So I'm going to say du dx equals 2x plus 2. You can do these in as few or as many steps as you want, but we're trying to solve for dx is essentially what I'm trying to do. So some of you will go straight from u to the differential, and some of you will take some step. It doesn't matter. I'm trying to solve for dx, and we'll get du divided by 2x plus 2 is equal to dx. I just moved stuff around. I just didn't write down that middle step. And if that bothers you, let me know, and I can write it down. But I took the dx to this side, and then divided by the 2x plus 2. So in order to take the antiderivative, we spend a little bit of time taking the derivative, which is what's going to drive us crazy in our heads. All right, here we go. Let's come over here and see if it actually works. Remember, I'm going to replace this with a u. So here's my integral symbol. In the denominator, I have a u squared. In the numerator, I don't have anything for the x plus 1, but that's okay. We're just going to cross our fingers that it goes away in a minute. And then at the end of our integral, we have a times dx. Well, remember, we just said dx equals du divided by 2x plus 2. Our hope is if we did this correctly, that all of the x's will go away. They'll cancel. We're not supposed to use the word cancel in math anymore, but I still use it. So that's why, you know. Does it? If we factor out that 2, maybe call me a cheater here, but I'm going to just erase this 2x plus 2 and write 2 times x plus 1, whatever you want to do there. I love this. X plus 1 on top, x plus 1 on bottom. What we could accidentally mistake, don't lose the 2. So we have 2 options with that 2. We can now stick it with the 2 with the u squared. My preference, slide it all the way out in front, but it's in the denominator, so it'd be a 1/2. And what's left in my integral, we've got the 1/2 out in front, is a 1 over u squared du. Which, if we're going to take the antiderivative, we should probably write it as u to the negative 2 du. Because the only time we use logs is if it's u to the first down there. This isn't a u to the first, it's a u to the second. So here we go, the 1/2 stays in front. I'm taking the antiderivative now. I'm going to add 1 to the exponent to get u to the negative first. Then I'm going to divide by -1, put that negative wherever you want. Let's see. I'm going to clean that up. Doesn't look great. That's okay. We don't have to do much, but me, I don't know why. I'm going to put the negative out in front with the 1/2, and I'm going to put the u back in the bottom. So I have a -1 over 2u plus c. And while that's so nice and pretty and simple, it's not our final answer, because remember, they asked us to integrate a function of x, and right now our answer is in terms of u. Easy fix. Just go put our x's back in. Slide it up. U equals x squared plus 2x minus 3. And don't forget, I still have that 2 down there in the bottom. Wherever you have that 2, you might have it as a 1/2 in front. That's okay too. There's our answer. Kind of like a little puzzle, isn't it? Kind of find a little space for everything. Could we check it? Yes, you can check it by taking the derivative. It's just that sometimes you have to do a little bit of simplifying to get it back to where you started. Okay. Awesome. What I want to go back to, and I'm kind of reference, is how do you know if your U is going to work? Here's what you should be looking for, and this may be something you wait until tomorrow or the next day to start thinking about, but if it is indeed the reverse of the chain rule, and what you've noticed is that every time this goes away, right? When you go to pick your U, you're kind of should be asking yourself, do I see the derivative of that U somewhere? Do I see a 2x plus 2 anywhere in here? And you know, if you think about it, you take out that 2, you do. That's kind of something you might want to consider. Do I see a function and its derivative? That's kind of one thing to think about. All right, let's take a look at this one. We got a product, we've got a composition, trig, thetas. Good stuff, huh? There's a lot going on here. So one of the things I said is, how do you pick U? I said, pick what's on the inside of something. Well, I've got a cotangent inside a radical, so there's something on the inside. We also, though, if you think about it, have a cosecant inside an exponent. So in this case, you're going, Miss Patton, which one are we going to use? Well, we could start with one, and if it doesn't work, we could go to the other one. It's not a great use of our time, but we could. The other thing we could do is what I was just talking about. Kind of, if you write it that way, you can see. So maybe ask yourself, do you see a function and its derivative? What's the derivative of cotangent? Oh, do we see a cosecant squared? It's negative, but yeah, we do. That's a great sign. What's the derivative of cosecant? It's cosecant cotangent, but that cotangent's inside a cube, so it's like a little. The good news is, I feel pretty good about that first one. And if it doesn't work, we'll try the other one, and that's frustrating to some of you, I know. So let's pick u equal cotangent theta. First of all, if you had to pick a piece of that integral that was messier than the other, can we all agree we'd pick the cube root piece? Cube roots are going to be a little more complicated than something squared. That's another kind of reason that you would pick the cotangent instead of the cosecant. But again, don't pick the cube root of cotangent. We pick what's inside, just the inside. Okay? All right, so John already said the derivative of cotangent is negative cosecant squared. So du d theta, not dx anymore because we're using thetas. So du d theta is equal to negative cosecant squared theta. And let's just move some things around. I'm going to multiply the d theta to the other side and then divide by the negative cosecant squared theta. So it's just some algebraic manipulation. So you will spend, and I'm kind of guiding us a little bit here, but you will spend time on these when you're doing them on your own, trying to figure out what to pick for you. I get that. That is going to be for some of you the most challenging part. And it's frustrating. I will just be upfront with you on that. That's why we're spending 3 days on this. Because I want to give you time to get a little bit of practice. It's kind of like factoring in Algebra 1. You didn't just do like 1 or 2 days. You spent like weeks on it. Because the more you did, the better you got, kind of thing. It's kind of the same thing here, unfortunately. All right, so whether we're using the pink line or the original, inside my integral, I have the cube root of, remember we called this u. We still have our cosecant squared theta. But then our d theta at the end is going to get replaced with du divided by negative cosecant squared theta. So I kind of ignored what I had written in parentheses, and I went back to the original integral. So again, this was my u, so I have the cube root of u. This we don't have anything for, that's okay. And then d theta is replaced with du divided by negative cosecant squared theta. We saw it coming though. Well, look at that. That should happen. If it doesn't happen, we should go check 2 things. We should go check to make sure we took the derivative correctly. That's the first thing. And then if not, we should check and maybe pick something else for you. Because I'm going to tell you, there's going to be times where you just don't pick the correct u. That's okay. Here's, don't lose this little negative. I like to circle them. And you know what? The very next thing I do is I slide it all the way out in front. Because I had a problem. I used to lose negatives in integrals all the time. So this is just my coping mechanism, right? Circle them, drag them out in front. All right, so I've got this negative. I've got my u to the 1/3. And then I've got my du. It's perfect. So easy now. There's no product. Beautiful. There's no trig. I think that's what we love about it. All right, so don't forget that negative out in front. We're going to add 1 to the exponent to get 4/3. We're going to divide by 4/3 or multiply by 3/4. Let's see. And that's another thing. We're just not used to that plus c. It's going to take a while, but without bounds, it's necessary. What I think you'll love about substitution is the fact that we can start removing trig functions, and with removal of trig functions, it just makes everything a little bit easier on the brain. All right, here we go. So last step, let's go put our u back in. So I've got negative 3/4 times the cotangent of theta to the 4/3 plus c. Gosh, these are fun, huh? different, but they're methodical, aren't they? Right? Pick a u, find its derivative, solve for dx. It's just a puzzle. Go put everything in its place. Let's take a look at this one. We've got a quotient, we've got trig functions, and we've got a composition because we've got something inside the cosine. Woo! And as we go on in this unit, I mean, today's lesson is on substitution. We're kind of like, well, I think we're going to use that method. As we go on, the struggle is going to be what method to use, but we kind of know we're going to use substitution. Question is, what should we try for u? Go ahead, Noah.
We just do x.
Great question. Don't write this down, but I love that Noah asked this. He said, can we just pick x? Okay, so if I say u equals x, am I going to simplify anything? Am I taking out a messy piece? No, but some people will say, I don't know what else to pick. So then we say du then would equal 1 dx. And so there's really nothing to solve for over there. We come over here and we'd have the cosine of pi over u all over u squared times du. And I love that Noah asked this because I see it happen all the time. But if you just pick x, did we actually change anything? Oh, we changed the letter, didn't we? But we didn't get rid of a mess. We didn't get rid of a quotient. We didn't get rid of a composition. But I was going to see it happen, so I'm really glad he said that. You should never say u equals x because it doesn't gain anything for you. It's not going to change or simplify anything for you. Okay? So we should always pick something that's a little bit bigger than x, even if it's just a little bit bigger than x. Remember my rule of thumb, pick what's on the inside of something. Do you see something inside parentheses, inside a radical? Do you see any parentheses? Do you see something inside those parentheses that's not just an x? It's like a pi over x. That's a great rule of thumb. Pick what's inside parentheses, what's inside a radical. So some of you are going, you just said not to just say u equals x. You're right, but this isn't just u equals x. It's like a 1 over x, right? And if that helps, go ahead and write it as pi times x to the negative first. Next step, take the derivative, which is negative pi times x to the negative second. So du dx equals negative pi x to the negative second. And if it makes you feel better, then call that negative pi over x squared. Even before we keep going, do you see this derivative anywhere? Look at our derivative is negative pi over x squared. Do you see something over x squared in here? Oh yeah, look at that. There's my over x squared. That's a really big clue that we're on the right path. Do you see a function and a piece of its derivative? Yes, the derivative of something over x will be something over x squared. That's a really big clue that we're on the right path. Okay, so let's finish, because remember we said we want to get dx by itself. So let's see, if I multiply both sides by dx, maybe take the x squared over and then divide by negative pi. So I multiply both sides by dx, then I multiply both sides by x squared divided by negative pi. Just moving things around. All right, so here we go. We've got our integral. Remember what I highlighted in green? That's our u. So let's make that replacement. So I have the cosine of just u. Already looks better. In the denominator, we have x squared. I don't have a replacement for that, so we'll just leave it there and hang tight. But we do have a replacement for dx. It's x squared times du all over negative pi. Which we love this because my x squareds go away. If they don't, that means we've done something wrong. Either we took the derivative wrong, or we manipulated it wrong, or we picked the wrong u. I'm just going to tell you, if it's going to happen, you're going to pick the wrong u, and that's okay. The more mistakes you make, the more you learn, and we hate to say that, but the more of these you do wrong, the more you're going to do right. It doesn't make sense, but the more you're going to start to see how this works. All right, you know what? This is a constant. Let's drag it all the way out in front just to get it out of the way. So for me, I have a -1/pi. It's in the bottom, so -1/pi. And the only thing left in the integral is the cosine of u du. I think, well, it's a little different. This is something similar that we started with today, because I think it was sine of u. We should be left with, if we did it correctly, we should be left with an integral that's manageable for us. There should not be products. There should not be quotients. It should either be power rule or something we have memorized. Oh, we have this memorized, right? Cosine is the derivative of sine. So I get -1/pi times the sine of u. We'll see. But we're not going to leave it that way. Put our x's back in. So my final answer is -1/pi times the sine of pi over x plus c. But notice I wait until the very end to put those x's back in. I don't put those x's back in before I take the antiderivative. The whole point is to simplify it so that we can take the antiderivative. So I don't plug those x's in until I'm all the way done. Good stuff, huh? I think I have time for the last one, don't I? So nice and simple. It's like the simplest looking integral we've seen all morning. There's no product, there's no quotient, there's no composition, right? But what is it asking? It's saying, what is the antiderivative of tangent theta? We don't know that. We don't know the antiderivative of tangent. It's not something I've asked you to memorize. Well, the only thing I think at this point, until we just say, what is the antiderivative? I think the only thing we can do at this point is put it into terms of things that we do know something about, like maybe call it sine theta over cosine theta. And now you're just looking at me like, okay, you've just made it worse. I get that. We've taken something as simple as a parent function and just turned it into a quotient. Because we had no other choice. If we don't know the antiderivative of tangent, we can't leave it as tangent. And just saying that u equals theta is not going to get us anywhere because we'll still be asked for the antiderivative of tangent. So at this point, we have a quotient, and it's pretty simple still, I think. But if we had to pick, for you, I'd pick what's in the denominator. So, and I'm going to write this down. When you're picking, I'll write it down here in a minute, but when you're picking your u, pick what's in a radical, in a parentheses, inside a trig function, in the denominator. If you have a choice, pick the denominator. Okay. So if du equals cosine theta, then du d theta is equal to negative sine theta, right? The derivative of cosine is negative sine. And again, this is where your head is going to spin. Because you're like, wait a second, are we doing derivatives? Are we doing antiderivatives? I can't keep those sines and cosines straight. I get it. I do. So let's manipulate this a little bit, and let's say du divided by negative sine theta is equal to d theta. I know I'm speeding up a little bit because I'm running out of time. I get that. Let's go put in everything we know. Remember, we said cosine is our u. So I'm left with sine of theta over u. And then d theta is equal to du divided by negative sine theta. Whoop, whoop. Don't lose that negative. And this is something I'm telling you, as soon as I cross those signs off, I'm putting something real big around that negative, and I'm dragging it out in front. If you have a feeling that you would lose it if you put it out in front, then maybe don't move it out in front, maybe just circle it. What am I left with? I'm left with a 1 over u du. That's so much nicer. We do know that antiderivative. We just talked about it. So we have a negative natural log of the absolute value of u plus c. So something so simple like tangent, like, oh, we should know. Well, we didn't know. We put it in terms of things that we could deal with. Use the substitution, and the last thing I'm going to do is go put that u back in. Not what we were hoping for. This is the antiderivative of tangent theta. Ooh. Not the nicest thing, but not the worst thing, by the way. Okay. So as you're writing that down, look at your last slide. It's just kind of putting some things that are important in one spot. You know, I like to do that so it stands out to us. So we just talked about tangent. So let's go ahead and write that one down. The integral of tangent x dx is negative natural log of the absolute value of cosine x plus c. It might be just faster to memorize that instead of turning it into sine over cosine and using substitution. But you can, doesn't matter. This one we already know, we've used this quite a bit today, but I thought it might be nice to put it in the same place. The integral of 1 over x dx, we've said, is the natural log of the absolute value of x plus c. These are the integrals that would be helpful. Well, the first one for sure you have to have memorized. And then cotangent. We didn't do it. We could do it by starting by doing cosine over sine, and then we'd end up with a positive natural log of the sine of x plus c. But again, you could find that antiderivative by just rewriting it as cosine over sine and then using a substitution. I know I sped up near the end there, okay? We did a lot of examples today, but I think all of those examples had something special about them, something different, which I think is important. We are spending 3 days on this. So if you're sitting there still going, I have no idea what's going on, let it sink in. Watch the video again. Go back and look at some examples. But we'll do more examples tomorrow in class. Tomorrow's class is all online, everyone. Join me at home. And yeah, we'll just let this sink in, okay? Hey, thanks for joining us at home. We will see you.